A 2-volt battery is connected to a parallel plate capacitor that has a plate spacing of 0.001 meters, and the region between the plates is free space. The battery is then removed without disturbing the charge on the capacitor, and you're told that the total energy stored on the capacitor is 1 joule. The first thing you're asked to do is find the electric field intensity inside the capacitor. Here we have the initial situation. The battery has been removed and there's some charge on the plates. We'll call that Q sub I, and the voltage drop across the plates is 2 volts. Since we are told to ignore fringing fields, the electric field intensity is only in the x direction, so to find the voltage across the capacitor, we integrate minus E sub I dx from the right plate to the left plate. So the voltage is the electric field intensity inside the plates times the plate spacing, or the initial electric field intensity inside the plates is 2,000 volts per meter. We are told the initial energy stored on the capacitor is 1 joule, so that will equal the energy density inside the capacitor times the volume of the capacitor, which is the plate area, times the plate spacing. So that initial energy density in the capacitor is 1/2 the permittivity of free space times the square of the initial electric field intensity. So now the plates are pulled apart to a spacing of 0.002 meters, and let's assume we do that without disturbing the charge on the capacitor. And now we're asked to find the electric field intensity inside the capacitor, the voltage drop across the plates, and how much energy is stored in the capacitor. Here is the situation after pulling the plates apart. Since the charge on the plate remains the same, we'll have the same electric flux density field after pulling the plates apart as we did before. So the electric flux density field is just that charge divided by the plate area. In other words, the charge density on the plates. This also means that we have the same electric field intensity between the plates after pulling them apart as we did before pulling them apart. We can find the voltage across our capacitor by integrating minus the electric field intensity from the right plate to the left plate. And we find that the voltage drop has increased to 4 volts. Since the final and initial electric field intensities are the same, the final and initial energy densities are the same. Since the volume of the capacitor has doubled and the energy densities are the same, it means we now have twice the energy stored on the capacitor, or 2 joules. This additional energy comes from the mechanical work you did pulling the plates from a separation of 0.001 meters to 0.002 meters. The plates have opposite charges on them, so they're attracted, so it takes work to move the right plate away from the left plate. So that mechanical work you did now appears as additional potential energy inside the capacitor.